So now, when we get to calculate fancier probabilities, we're going to talk about experiments with equally likely outcomes. So that's all we're going to look at from now on. When I flip a coin, every outcome, every result has an equal chance of happening, even though there are different outcomes. Heads or tails, the same likely. It's equally likely. If I roll some dice, let's say 2 dice, every pair of numbers is equally likely. They all have the same chance of occurring, but I have different possibilities. So that's what I mean by an experiment with equally likely outcomes. Every single outcome has the same probability of occurring. So then when we're talking about the probability of an event, this is how we're going to calculate it. Now what does this mean? This means the number of outcomes in my event E divided by, so I'm making a fraction, divided by the number of outcomes, let's say with no restriction. That's all I'm going to use from now on. Yes, probability in general can get fancier than that, but this is where we're going to stop. It's more than sufficient to practice what we're trying to place an emphasis on, which is the problem solving and the way of thinking. We're just using counting probability to practice that. Everyone, are there any questions on what this in the box means and how I'm going to calculate a probability? So the reason why I say that it's nothing new is because we've been doing these things. We've been counting the number of ways to get something, the number of ways to get something with no restriction. Now, to calculate a probability, I just do 2 of them and make a fraction. That's all we're doing. So it's literally nothing new, except there's a fraction. So when we're actually counting these things, I always want to do the bottom first. That's just my recommendation. And as we're looking through examples, as we're working through examples, it should become clear why I want to look at the bottom one first. So it's something to keep in mind. So let's look at times. Let's look at our next example, which is number 3. So it is good news and bad news. The good news is that I'm still just counting. The bad news is that I'm still counting. And I have to be comfortable with what we've done previously, the first 5 sections, before I can fully understand all of this. Let's look at example 3. So a normal die is rolled 5 times in succession. Each sequence is equally likely to occur. What is the probability of some stuff happening? So what is an outcome of my experiment? That is question 1. I need to understand what the experiment is and what do I have as a result of the experiment. What is an outcome in this case? Give me an example. There, give me an example of something. You're doing this experiment. What do you have as a result? Seems like such a silly step, but doing this step makes things so much simpler. So you're just going to have to humor me and give me some examples. Because only by making an example do I really know for sure that I understand what I'm looking for.
3, 3, 3, 3, 3.
3, 3, 3, 3, 3. Everyone happy that that is one possibility? So what is an outcome in general? It's a sequence of 5 numbers, each ranging from 1 to 6. Now whether I write that down, or whether I tell myself what it is, whether I tell someone else, it's an important step. Because if I skip this, and I'm not sure what I'm looking for, the rest is not going to work. Now, I want to look at the restrictions. They want, in the first restriction, A, no 6. So let's define an event. We'll call it E. Now instead, I'm just giving a name to exactly what they're asking. So I don't have to write the whole thing again. They have it in their question. So all I'm going to say is that E be the desired event. It's just a formality so that I can talk about the probability of this event. Some books, depending on what you're looking at, they write it as P, maybe not even round brackets, and then they put the words in here. It's just sloppy and it's going to get confusing when I combine events. So to save myself the possible confusion later, it's just sort of a formality step. Give it a name, whatever they're looking for, I give it a name, and then I talk about the probability of that happening. How do I calculate the probability? For now, I'll emphasize how, so I remember. I count the number of ways E can happen, and I divide it by the total number of ways without any restriction. Well, I said, do the bottom first. I'll always do the bottom first. If there's no restriction, how many ways can I get a sequence like that? I hear a very soft 6 to the power of 5. We should really be happy about that by now. We really should. There are way more complicated things. The no restriction ones, regardless of the question, should be straightforward. Really should. So I do this first because A, it's easy and I feel better about myself. And it just gives me a reminder of what the experiment is. Now I go to the top, and now I have a restriction. And the added restriction is no 6. No 6 can be wrong. So that's a valid one. I can't see a 6 anywhere. How many ways can that happen? 5 to the power of 5, he says confidently. Why?
Because you don't have a 6 anymore, so that means there's 5 numbers you can use. 5
choices every time instead of the original 6. Pretty straightforward, I think. And wear black when you're working with children. Any questions on that? So it's just counting all over again, except I have 2 pieces in my fraction. The bottom one will always be straightforward if I understand what the experiment is. It's the top one that has the restriction. Any questions on this? That was A, so let's do B. All the numbers are the same. I have a different restriction. Let's call F the desired event. so that I can talk about the probability of event F. I remind myself that the number of ways I can get to this restriction divided by all possible ways. Well, all possible ways first, well, it's the same experiment, so it's going to be 6 to the 5. Nothing changed, only the restriction changed. I'm still doing the same thing. Now I have the restriction, all the numbers are the same. Let me just move this guy down a little. So I have more space here. All the numbers are the same. Now this is just my start example. The basic method. Depending on the restriction, the way I'm going to count this, breaking it up into steps, is going to be different potentially. The restriction leads me to my strategy. If all the numbers should be the same, can I break that up into a first step followed by another step? What would I like to know first if all the numbers should be the same? It's hard, I put you on the spot, I look right at you, it's hard. What could a first step be? No? Nothing? Let's make an example. If you give me nothing, I'm going to torture you with an example. That's too many. This is the penalty. Now you have to give me an example. He says 4, he was first, sorry. I'm going to go with his 4s. So what did you decide on first before making the sequence? Which number? So step 1 could be choose which number. There's only one number that's going to appear. Choose which number will appear. How many numbers do I have available to choose from? 6. How many do I choose?
1.
Number of ways to do that? 6, choose 1. I choose which number. Before making the sequence, he decided on a 4. And there was 6 choices. There were 6 choices, and he picked 1. Now, once I have the 4, what do I really have? I just have my numbers floating around. And this example, it's 5 4s. I need to make a sequence of these 5 numbers, so I need to arrange them. Now, even though this is simple, and I can do this in a more simple way, I want to emphasize the steps so that when things become more complicated, I'm used to breaking it up. How many ways can I arrange these 5 numbers? 5 factorial? Five of them are identical. And if some things are identical, I need to divide. Now you could have just said there's only one way to arrange the 5 4s. 4 4 4 4 4. There's nothing to do. Swapping 4s will never give me a new arrangement. But technically I am using that formula for when things are identical. Any questions on this? So I'm just practicing more counting examples, really. The fact that I'm talking about probability doesn't really make this any more or less complicated. Awfully quiet. All the numbers are different. Let's call this event G, EFG. Then I can talk about the probability of event G. Remind myself, how am I going to calculate this probability? Fraction. Let's do it over here. Experiment's the same, so the bottom is the same. Now what am I looking for? All the numbers are different. All the numbers are different. What can I do? Well, let's go with my example. How can I build up, systematically, build up a sequence? For those that have come to office hours, I emphasize selection, then arrange. So what do I do first? I didn't ask for a number, I asked for what do I do? What is step one? Not sure what I do. 3 words. I need to select the numbers first. They're all different, but there are many numbers. Not all of them will appear in my sequence, not too many. I have 6 and there's only 5 positions. So some numbers won't appear. So let's just get the numbers together. For example, 5 numbers. How many ways can I choose 5 numbers? That's one example. This is my step 1, just getting the numbers together. How many ways can I do step 1? Let's here select the numbers. How many ways can I complete step 1? I'm choosing 5 numbers of the possible 6. My available numbers are 1, 2, 3, 4, 5, 6. I need to grab 5 of them, and by doing that, I guarantee that they'll all be different. 6 choose 5. But ultimately, my experiment says make a sequence, so I need to follow that by the arranging step. How many ways can I arrange these 5 numbers? 5. Are there any identical ones? So I don't need to divide by anything. For example, 5, 6, 3, 4, 2. Doesn't matter. Update my example. Now I have a sequence, so there's no more steps. But now you could have done 6 times 5 times 4 times 3 times 2, and it's the same. But as soon as I make this more complicated, placing a restriction on the selection, placing another restriction on the arrangement, that method will never work. Never. So by getting used to separating selection from arrangement, or from arranging, I'm able to handle more complicated questions without doing anything different. So I practice that with the simple example. But there is more than one way to write these things, usually. I'm looking for the way of thinking that I know is going to help me for the other questions, other restrictions. I want to minimize jumping between different methods. If there's a method that works more often than anything else, I want to use that consistently to take the guessing out of it. And this selecting, then arranging strategy works more often than anything else. Nothing works every single time. It depends on the restriction. But getting used to that way of thinking, select, then arrange, is the best way to go. Any questions on this number 3? So I'm not doing anything strange. I'm just putting this no restriction 1 at the bottom. And that's my probability. It's essentially just more practice for the previous sections. So, at the risk of demoralizing you even further, I remind you that the midterm is not that far away. There's good news and bad news. I usually put the midterm after spring break. This time I thought, no, let's put it before, get it done, then you can relax. But that does require that we work a little bit more now when we're done with midterm 1, you never think about phase 1 again. Only midterm 1. Well, not never. We'll probably, yeah, let's say never. Make it simple. Yeah. Pretty much never. But it is important that if you're not up to speed, to take this time to catch up, because we're not really doing anything new. You have time to catch up before midterm comes. Yeah. Any general questions, concerns, comments, complaints? Okay. Number 4. An urn contains 5 red, 6 blue, and 8 green balls, all different sizes, so they're all different. You can tell them apart. Pretend they're numbered. If a set of 3 balls is selected at random, so I just grab them, what is the probability of some properties occurring? So what is an outcome? I'm going to emphasize the step more and more because it's an important step that it seems that we're glancing over, but I don't want to skip this step. I need to understand the experiment and what I'm looking to count. What is an outcome of this experiment? In other words, I'm doing this experiment, doing what they described there. What do I have as a result? 3. Yeah, they're not colored. It's a selection of 3 balls. Could they be the same? Could they be different? Let's say different sizes. They're not happy that they're going to be different. How do I know they're going to be different? It has to come from the way I'm doing the experiment. So you know, at my age with this fan above me, I can't hurt.
Because each of the balls are different from each other.
Yes, they're all different. I'm not worried about the color. How do I know that my selection will have 3 different balls? Why can't 2 of them be the same? It's because I'm grabbing 3 of them. If I grab 3 balls, they're going to be different in my hand. Don't worry too much about that. Let's just think about this. It's going to come up. The no restriction ones, let's just do it now. Get it out of the way. How many ways can I select 3 balls if there's no other restriction? I have 19 in total. I need to select 3. 19, choose 3. All right, now I'm looking at the specific restrictions. I did the bottom first, we just did it separately. So now let's look at A, let's call it event E. New questions, or I can start with E again. E for them. Whatever they're asking, I'm just giving it a name. Not doing much. Probability of E. Well, it's going to be something over 19, choose 3. That's the bottom. Did the bottom first. And let's just practice for me to make sure I understand what I'm counting. I'm counting selections of 3 balls. Now I want to count the number of ways I can make the selection such that they are all the same color. Now, I want to break it up into small manageable steps so I systematically build my selections. The smaller the steps I can break it up into, the easier each piece is going to be. Putting them together is just multiplying, so that's not a problem. What could step 1b? I want them all the same color. If you have to make an example, give me an example. No. Well, sorry, let me backtrack a second. Give me an example at the end, I guess, over here. I'm just selecting, so there's no arrangement of any kind. Let's suppose they're numbered. Instead of sizes, let's have numbers, but I can tell them apart. Give me an example of something you could have selected under this restriction.
3 blue ones.
3 blue ones. Let's call it blue 1, blue 2, and blue 3. So what could be a first step? What do you need to decide on to get your
I
example?
have to choose a color.
You need to choose a color first. How many colors are available?
3.
I need to choose one of them. So what do I know at the end of step 1? Well, she knew that she wanted 3 blue ones. She didn't know which ones. There are 6 blue ones. I'm not going to select all of them. But I need to decide on which color will be in my selection first. It could be blue, it could be red, it could be green. This is one step on the way to the end result. What do I need to follow that by to get to the end? To get to an actual selection? I know the color. What do I need to do now? Select balls of that color.
There's 6 blue, choose 3.
Yeah, but I don't know what's blue. This is just an example.
Well, from my example, it would be
Yes. If I knew it was blue, it would be 6, choose 3. But what if someone else picked red? Then this isn't right anymore. What if someone else picked green? Then that's not right anymore. We see the problem. We're making an attempt. We have the right idea, but it seems like I can't put them in one expression because the number of balls of each color is different. I have 6 blue ones, and I have 5 red ones, and I have 8 green ones. I do need to select the color first, but depending on the color, the numbers change. So it seems like this is let's say here, not correct for all the colors. Sometimes by making a mistake, we learn more. We see what we need to do. So it seems like because the colors are all different, the total number of each color is different. I'm going to have to separate them into more specific pieces. So probability of B, 19, choose 3. I want us to really focus on these 2 examples, 4 and 5. We'll do 5 next time. They illustrate a lot of things. So instead I'm going to say, let's just select blue, or red, or it could be green. How many ways can I select all 3 blue marbles? Now I know it's blue. So 6, choose 3. Am I done with my experiment? What do I have as an example here? I've selected 3 blue ones. Blue 1, blue 3, blue 2. Am I done? Do I have a selection of 3 specific marbles? Blue? Balls, not marbles.
Now you gotta do red.
No, just answer my questions. Am I done? Do I have a selection of 3 balls? No? They're right there. Blue ball number 1, blue number 3, blue number 2. We're done. I've selected 3 balls. I'm done. With that possibility, there are other possibilities. So I need to add this number to the other cases, not multiply, because I don't follow this by another step. I'm done with my selection. If I knew it was blue, could be red, could be green. So these are different cases, different ways of completing my whole experiment. So I have to add them. Yes.
Is it possible to do like, I don't know if it is, but like 5, 2, 0, or like 8, 2?
Yeah, absolutely.
Oh.
I could show more detail here and say I select no red, 3 blue, and no green. That might be better. To emphasize that I am going through all the colors and I'm only selecting blue. So let's do that, yeah? Let me move this guy a little bit to the right. Now, the case where they could be all red, now I select 3 red ones, no blue, and no green. So you could see it as little steps, and when I've completed this, I have completed my experiment. This is one way of completing my experiment. This is another way. They don't overlap. In this case, they're all blue. In this case, they're all red. In this case, they're all green. The green case will be 5, choose 0, no blue, no red, no blue, 3 green. Each time completing the experiment, but doing it in different possible ways. So I need to add all those possibilities together because they all fall under the restriction that all 3 marbles are of the same color. We need to understand why we're adding those 3 things. Yes?
Do you need to put 5 or choose 0?
No, you don't have to. She just wanted to show that I am doing little steps. If I can be more complete and show that I'm covering all the little steps inside this case, why not? Why not write it down? Anything choose 0 is just 1. There's only one way to choose nothing, I do nothing. So it doesn't change the number, but it feels a little better to be complete, list them all. But you don't have to, no.
So if you were going to do that, you would just have 6, choose 3, plus 5, choose 3, plus...
So if you don't like the choosing 0, you could say, 6, choose 3, all blue, or all red, or all green, over the total. So it's not step 1, choose 3 blue ones, followed by choosing 3 more. This one is the experiment done. This is a different way of doing the whole experiment because I end up with 3 specific balls. This is a different way of doing the whole experiment. So I add the 3 different cases together. It's not followed by, it's one or the other. Let's see if we have time for the next one. It's not crucial. So okay, let's leave it here. Let's go think about this. And try and do 4B. Try and do 4B. And we'll do it next time. Try and understand why it's plus. And why we can just put this in one little expression. It's going to be totally different.